Hey, Ryan here with learnometrics.com, and today I'm going to show you why units are an engineer's best friend. As you've already encountered in your physics and calculus courses, there are two types of unit systems. There's the English system and the metric or SI system. And I bet that you probably like the metric system better. Why in the world do we even have both systems? Well, there's a mix of reasons, but one of the main ones is that it's a result of our history and tradition. It's already been there. The reason why we still have it today is because of political challenges going all the way back to 1790. Thomas Jefferson, then U.S. Secretary of the United States, decided to use the imperial system instead of switching to the metric system, which the rest of the world was already adopting, because big business lobbied against changing to the metric system because they would have had to rebuild or repartition all their machines from English to metric. Using a different unit system doesn't just affect you as an engineering student. Rocket scientists have screwed this up before. Using a different unit system has real world consequences. You may have heard about the Mars Climate Orbiter. It was built using two different unit systems. The first was the control systems for the spaceships. So this is internal calculations that the spaceship would use. They used metric for that control system. The second is ground control on Earth. So they send a signal to the spaceship and tell it what to do. Ground control systems was built using English. What happened is engineers didn't use the ground control until 4 months into the mission. Once they started using it, it really quickly started to introduce errors. And the reason for that is because 1 pound force in English, which was the ground control, is the equivalent of 4.45 newtons to the spacecraft. This means that after 4 months, every single calculation that they sent to the spaceship was off by a factor of about 4.5. And so you can see here, this top trajectory is what they thought was happening. They thought they were going to end up 226 kilometers away from the Martian surface. What actually happened, because their thrust was so much stronger, when they were positioned to get into orbit, they ended up way, way closer at 57 kilometers, which is about 226 divided by 4. So close to that conversion. When they tried to do the landing sequence, they lost contact with it. It crashed because when you're 160 kilometers closer to something than you think you are, you're done so. This ended up being, with inflation, I'll do it in green, a $530 million mistake. Somebody got fired and blacklisted from the jobs. So the moral of the story for units and for most things in life, do it right the first time, make the hard decision, fight back against the lobbyists or whatever, or you may screw people over 200 years in the future. And the second moral of the story, you're never too smart to double check your answer. Let's look at the type of units you'll see in your statics course. This is a chart of the SI system of units, very neatly laid out. It doesn't have everything here, but it's a great starting point. There are two types of units that you'll see. You'll see base units. Think of these as different ways to measure the world. If I measure length, that is different than measuring mass, which is different than measuring time. They're just completely different dimensions of the world. So your base units that you're going to want to focus on for your statics course is going to be length, mass, and time. Meters, kilograms, and seconds. Or in English, feet, pound mass, or slugs, which I'll explain later, and seconds. Seconds and time is the same in the English and metric system. We didn't screw that one up. These other ones don't matter for this course. The prefixes that you'll need to know, and recommend memorizing these early on in the course. It'll make your life a ton easier. You need to know giga means 1 times 10 to the 9th. Mega means 1 times 10 to the 6th. And kilo means 1 times 10 to the 3rd. And you also need to know that it's G, M, and K for the prefixes. So that would be, if I have giga Newton, that means it's 1 times 10 to the 9th newtons. Or another way of writing that is 1e to the 9 newtons. The other things you'll need to know is you'll need to know milli, micro, and nano. Just memorize these. Do it early. Make some flashcards or just have a little table beside you when you do your problems. It'll save you a lot of work if you know these well. The next type of units that you'll encounter is derived units. These are units that are built out of combining the different basic units. So let me put those here on the side. So we'll have meters, mass, and time. So the first one is going to be force. Force has the units of newtons. One of the tricks that I always use, if I forget what a newton is, which does happen, I know that force is equal to mass times acceleration, because the force of gravity is mg. So mass has units of kilograms, and acceleration has units of meters per second squared. So I know that a newton is equal to kilogram times meters per second squared. That's just a trick you can use to remember them if you forget. Another unit you'll encounter in this course is a moment, which is a Newton meter. Which from above, that's going to be kilogram times meters per second squared times meters. The next one is going to be moment of area. This is going to be around the middle of the course, or sorry, moment of inertia. This one is going to be kilogram times meters squared. This one doesn't have a derived unit in it. It's just a combination of base units because there's no newtons in here. There's nothing where you need to rewrite it to understand what's going on. And the final one is going to be the area moment of inertia, which is going to be meters to the fourth. Now, one of the things I'm going to try to do in this course is help you build your intuition. So this force term here can be either positive or negative. You can have positive or negative forces because force is a vector. Moment can also be positive or negative. Moment of inertia can only be a positive term. And the reason for that, mass has to be positive. You can't have negative mass. And distance is going to be distance squared. And if anything's squared, then it's positive. So moment of inertia is going to be a positive times a positive, which means it will always be a positive. Same thing with area moment of inertia. If I break this down, this would be m squared times m squared, where this area term here, because area is a distance times a distance, is replacing the mass term from the moment of inertia. This is otherwise referred to as the mass moment of inertia for the reason I just explained. So this will also be a purely positive term when you encounter it. So in summary, I would recommend memorizing force is newtons, moment is Newton meters, mass moment of inertia or moment of inertia is kilogram meters squared, and area moment of inertia is meters to the fourth. Just have that in a chart somewhere. Everything we've looked at so far has been in metric. I'm going to show you with this chart here how to convert to English. So time, there's no conversion needed. Metric and English have the same. That's great. For length, I would recommend just memorizing a few of these. This one would be a great one to memorize. This one is the one that I used for my basically entire engineering. It was 1 inch is equal to 2.54 centimeters. And then memorize the mile conversion. 1 mile is 5,280 feet, 1.609 kilometers, or 1,609 meters. Acceleration, memorize this one. Gravity is 9.81 meters per second squared, or 32.2 feet per second squared. Mass. Mass is the most confusing part of the English system because there's two ways to refer to mass. There is the slug, and then there is pound mass. In English system and a lot of your problems, there are 2 pound units. There's the pound mass, like I said here, and there's also the pound force down here. They are different. The way they're related is that 1 pound mass times 32.2 feet per second squared is equal to 1 pound force. So what I'm going to do in this course is I am always going to label with the subscript, if we're using English units, M or F, so that it's abundantly clear what we're using. In force, everything here is pound force. In work and energy, everything here, if you see pound, it's pound force. In power, it's pound force. And in pressure, it's pound force. So just keep that in mind with the English system. There is pound force and pound mass. I will always label them, but in your own homework or in your own classes, your professor may not be as kind. The next unit topic is going to be translation and rotation. So this is specifically comparing how they're similar. I doubt this will come too into play in your statics course, but this is a nice reference chart to refer to in the future. The big difference between translation and rotation is that translation is in units of meters, or meters per second, or meters per second squared. Rotation is in units of radian, or radian per second, radians per second squared. And if you ever need to convert between radians and degrees, here is a wonderful chart for you for figuring that out. 90 degrees is the equivalent of pi over 2 radians. is just a nice visual of how to relate radians to degrees. Degrees is the English, radians is the metric. If you are wanting to convert it from an equation, let's say you have like 1.5 radians, what you would do is 1.5 radians times 360 degrees over 2 pi radians. That's the conversion factor, 360 over 2 pi. And then that would give you, if I have my calculator here, 848.2 degrees for your answer. Down here, if you want to go back from degrees to radians, then you'd have degrees canceling out, and you'd have x over 360 times 2 pi, which would give you whatever your answer is. All right, now we're going to do a quick example problem, and I'm going to show you to convert this. The first thing that I would recommend if you're doing unit conversion, you may have seen this in chemistry, draw a long straight line, and then draw vertical lines wherever you have unit ratio. So I'm starting with 1 kilometer cubed per hour. I need to get this to miles cubed per second. I'm going to start with the hour because that's easier to do. I'm going to do 1 hour is 60 minutes, and then 1 minute is 60 seconds. And then I can go through and I can cancel out all the units that I don't need. So now I've converted from hour to second. Now the next thing I need to do is I need to convert kilometer cubed to miles cubed. I'm going to scroll back up. Now you see here, I have 1 kilometer equals 0.6214 miles. That's great. So I'm going to use this 1 kilometer equals 0.6214 miles for the conversion. So I have 1 kilometer in my base equals 0.6214 miles. Now you'll notice I have kilometers cubed here, which means to cancel that out, if I do this right now, I would be left with kilometers squared. So I need to do it 3 times. 4 miles, 0.6214 miles, 1 kilometer. This way, I have fully canceled out this kilometer term. The alternative way to do it, to take up less room, which I think most of you will do in the future, is I would just cube everything in here. So cubed, 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 cubed. That means I would have kilometers cubed in the denominator and miles cubed in the numerator. Be very careful about making sure you cube the numbers as well. That is a very common mistake, is to not cube those numbers. But if we do this, then our answer is going to be 6.67 e to the negative 5, or 10 to the negative 5, miles cubed per second. So that's 1 kilometer cubed per hour is equal to 6.67 e to the negative 5 miles cubed per second. Intuitively, that makes sense. I'm going to check my intuition here. I'm going from hour to second, which means I would expect it to be much smaller. And I'm going from kilometers to miles, which I'd also expect to be smaller. So this small number makes intuitive sense to me. That's it for this episode on units. I hope it was helpful. Make sure you either screenshot the sheets or head over to the course and you can download the PDF version of those unit sheets with some extra advice. Next up, we're going to be working with vectors.